Bismillahirrahmanirrahim. Assalamu alaikum. So, as we discussed earlier, that we can have different kinds of integrals. We can have integral of a function which is deterministic functions, and we can be asked to integrate it with respect to some other deterministic function. So that lies in your calculus. But then we had said that we can also be asked that we have a function which is deterministic, but we we want to integrate it with respect to something random, let's say Brownian. Then a more general question that can be posed is how to define stochastic integral, let's say a to b, for a function which is deterministic. Now the function itself uh, is random, unlike we had deterministic in this Weiner integral. So now if we have the function that we are integrating is random, and we want to integrate it with respect to something which is also random, so we are basically integrating something random with respect to some other random quantity. And previously when we were doing Wiener integral, we were integrating this function which was deterministic, but we were integrating it with respect to something random. Now we are more general, so we have random function and we want to integrate it with respect to some other quantity which is also random. So this is going to be the general integral that will be called stochastic integral. So this is stochastic integral. Because this function that is integrand that we want to integrate is random, so I will be using the word process for this. So I have a process, random process, and I want to integrate it with respect to another random process. The question is how to define this nice quantity. So before we start this, I want to fix some of the things, like I want to fix Brownian motion and filtration that will satisfy certain conditions, and I also want to fix uh, function space or functional space that we will be working in. In other words, the function or the process that we want to integrate have to have some properties, and what are those properties, I want to talk about them as well. So firstly, uh, the Brownian motion that we will assume before we define this is b of t, and this is Brownian, and we have a filtration ft which is filtration. So we want these two mathematical quantities to satisfy these two conditions. Number one, for every time t, for each t, this Brownian is ft measurable. In other words, this process is measurable, so b of t is measurable in the filtration ft. Number two, for any s less than equal to t, the random variable p of t minus b of s is independent of sigma field fs. What does this mean? This means that if you want to compute the expectation, for example, of bt minus bs given fs, so because this is independent, so it is going to be expectation of b of t minus b of s, which is again 0. So these two assumptions are to be satisfied by these two quantities. So before I define my stochastic integral, I want to have my Brownian motion and filtration to satisfy these two nice properties, or they need to obey these assumptions. Additionally, I will define a function space which is L to AD of AB close interval times this omega. Because my functions are multivariables now, my processes, my random processes that I want to integrate are multivariables because they depend on t as well as omega. So this t will be coming from this and this omega will be coming from this. So that's why I need to define my space in such a way. And this space is called the space of stochastic processes. One can show that this space is Hilbert space, and it's the space of those functions which are roughly speaking square integrable, and the sense we will be defining the sense later on. So secondly, what other quantity I want to have in my f of t comma omega is, number one, my f of t comma omega. So this random variable that I want to integrate, or this process that I want to integrate, should be adapted to filtration ft, and the filtration is the one that I have defined recently. Secondly, the integral of expectation of this f of t squared dt should be finite. So basically this quantity is somehow, I can write this quantity in this way as well, a to b, and then integral over omega of this f of t squared dp and then dt. So like it's a kind of somehow roughly speaking it's a norm on this, like, so whatever I need to have my this quantity to be finite. Okay, we will see whether it's going to be norm or not, but what we need is our process should be adapted to ft, and this quantity should be finite. So in the next videos we will define stochastic integrals, but and those stochastic integrals are f of t comma omega will be satisfying the following assumptions that I defined, or b of t will also be satisfying the assumptions that we have defined, and our filtration will also be satisfying some properties that we have defined in this video in the start. Next, let's meet in the next video for the stochastic integral. So far, take care of yourself, keep subscribing my channel. Allah Hafiz.